Okay, guys, I'm going to try and summarise Unit 9 for you. I'll put it all together like this as well. I'm going to email a copy of this to Chrissy, who can show you what's going on. But let me try and bring it together. Unit 9 is about forces, particularly F equals ma, Newton's second law. Force equals mass times acceleration. It's the most important formula ever. Always come back to thinking about F equals ma. Always come back to this. The F in it is the resultant force, So, it might be there's only one force, no problem. It could be that there are two forces acting against each other, 8 newtons, 3 newtons. The result, 5 newtons that way. Easy, but could be needing to add forces. You may have to draw a free body diagram, The only forces I'm interested in are the forces on one object. Let's say the mass on a string. I'm only interested in the mass. So just draw the forces on the mass. If mg is bigger than t, the mass will accelerate down. If mg is equal to t, it will remain at rest. Yeah, if it's 0, if the resultant force is 0, it remains at rest, or it continues moving in the same straight line it was in. If the resultant is 0, it stays at rest, or it continues moving in the same straight line it was in. If the result is not 0, it accelerates. If the ball is too heavy for the string, the ball will accelerate downwards. Okay? Right, so what is acceleration? Acceleration, you know, it is rate of change of velocity. Change in speed, change in velocity divided by time. Change in speed divided by time. Why v and u? Well, because v is the final speed, u is the initial speed. V is the final, u is the initial. Take one away from the other, you get the change. Why speed and velocity? Velocity is a vector, speed is a scalar. Speed has a number, 5 meters per second. Velocity has a vector, 5 meters per second in that direction. 5 meters per second west, or whatever. So vectors have direction as well as number. Scalars just have number. Speed is distance divided by time, of course we know that, but we use s for distance, by the way. Speed is distance divided by time, we know that. But what if the speed keeps changing, as it often does? We're dealing with acceleration, remember. If the speed changes, we have to do average speed equals total distance divided by time. So look, there's loads of formula in here, you've got to learn them. What about representing speed change on a graph? Oh, how cool is this? What rubbish. What about speed change on a graph? Put some numbers in, 2 and 5, 0 and 3. Okay. How would we do acceleration? Change in speed divided by time. Change in speed, 2 to 5, 3. Divided by time, how long does that take? 3 seconds. And don't forget that unit. Units everywhere. This is where you might fall down. So always think, have I got the right unit in there? How might we get distance travelled from here? Area under the graph. This is as complicated as it gets. And look at it, it's a rectangle and a triangle. 6, 1. Okay? Not many ideas. What if I want to stop a car? We deal with safety here quite a lot. We want to stop a car. We've got to react to the fact that we need to stop it, and then we need to use the brake, and the brakes have to do their job. So why would the car travel while we're thinking, while we're reacting? Because of its speed and because of various other things. The more these are involved, the further the car will travel. Here, How far will it travel once you put your foot on the brake? Depends on these things. Obviously, the more gravelly the surface, the worse the tyres are, the further the car will travel. It's all about safety. Those are, I think, obvious. What about this business of momentum? The only reason it's in there is really for safety again. You can do a quick rearrangement to get this momentum idea, momentum at the end minus momentum at the beginning. What is momentum? Definition, mass times velocity, that's it. So, if we want to stop something, we've got to take its momentum and reduce it to zero. How do you do that? Well, you apply force for a time. And you want the force to be small, you want the time to be big. And that's what these are about. They're about making the time bigger. If they're lead, you don't carry them in metal containers, because when you stop, they stop dead. You carry them in cardboard, because when you stop, the cardboard crumples, crushes. Anything that will squish is good. Okay? That's the only reason momentum's in there, guys. Risk. There's a little bit about risk. It's blatantly obvious, but let's just think about it anyway. Russian roulette, 1 in 6 chance. If you don't know what Russian roulette is, that's a good thing. I'm not going to tell you. But the chance is 1 in 6 of the chamber is filled. 17%, same thing, 1 over 6 times 100. Roller coasters. When you get on a roller coaster, if something goes horribly wrong, there's probably more chance of you dying than Russian roulette. But why do you do it? Because you've seen people do it before, you've probably done it yourself before, and also you know that somebody has had to think about safety. So we take risks, but we assess the risks. Finally, look, there's another law, a Newton's third law. It's about forces. Nothing to do with motion. Forces occur in pairs. Whenever the book rests on the table pushes up on the book. By definition, if the table pushes up on the book has to push down on the table. Nothing to do with whether it's going to rest on the table, bounce off the table, fall through the table. No, it just, when it's in contact with the table pushes the book pushes the table. These are called action and reaction. Good luck, guys. Hopefully, more to come.